The name of this video is Lorentz force relativity dual. This is the third and last video for Lorentz force and relativity. And so let me remind you that we are considering a quasi-filiform wire carrying a steady current I. So now we want to be in the reference frame F prime, which we already investigated in the video called charge relativity. So this is the back end of the wire here. This is the wire itself, which is shorter than in the first video because now we are in F prime, special relativity. This cross-sectional area here, as always, is capital A. We consider a cylindrical coordinate system with z-axis coinciding with the longitudinal axis of the wire itself, which again is quasi-filiform. So this is z. This is the r-axis. This is the origin. This here, right-hand rule is var phi, as always. In the reference frame F prime, we are on the particle, the single point-like charge particle minus q, which therefore is now steady stationary, does not move, because we are on this particle here. This is our reference frame. Therefore, the wire itself moves at a velocity towards the left, v, in this fashion. And we already assume that v and v naught are the same velocities. So in this case, it thus happens that rho plus prime move at a velocity v equal to minus v, as we have seen in the previous video, whereas now the rho minus prime move at zero velocity. They do not move. As we've seen in the previous video, the wire, however, moves. So in this case, since the rho plus prime are the particles actually moving, by definition, the current I prime points in this direction. This is I prime in F prime. Now, the first question is, we have a non-moving particle minus q with a current I prime. The current I prime definitely generates a magnetostatic field B prime. But is there a Lorentz force associated with this? There is no Lorentz force. And why is that? Because the velocity of minus q is zero, because minus q is steady. So there is no Lorentz force. There is no magnetic component of the Lorentz force in this case. However, in this case, we know that the wire is not anymore uncharged. W, the wire, is charged. And what is the volume charge density of the wire in this case? We calculated this quantity in the previous video, and we know that rho wire prime, which is rho plus prime plus rho minus prime, is given by v squared divided by c squared times alpha times rho plus, where I remind you that alpha is equal to the square root of 1 minus v squared divided by c squared, the relativistic coefficient we already introduced in the previous video on charge relativity. So rho w prime is equal v squared over c squared alpha rho plus. We calculated this in the previous video. This is great. So now the wire is actually charged in F prime with this volume charge density. Now, if I give you a quasi-filiform wire with this volume charge density, how can I compute from that the linear charge density lambda associated with the wire? Well, lambda wire is clearly given by rho in the reference prime is given by rho w prime times the invariant quantity, which is the cross-sectional area A. That's what it is, okay? Clearly units are correct, because this is charge coulomb over meter cubed times meter squared is coulomb over meter, which is lambda w prime, okay? Even the units, let's write it down, is coulomb divided by meter, which makes sense. All right, so now we know that we have a quasi-filiform wire, indefinitely long, with a lambda w prime given by this equation here. So we can clearly calculate the electric component of the Lorentz force, which in this case is F. Well, first of all, we want to compute the electrostatic field E due in the reference prime, due to lambda prime. This we calculated in the beginning of 242 in many different ways. The result, I remind you, is in the denominator 2 pi epsilon naught r. In the numerator, we have lambda w prime. The direction is radial. Now, the Lorentz force associated with this field, F prime, has to be equal to the charge, which is minus q times E prime. And so, the force F prime in the prime reference frame is given by minus q, so it's minus q divided by 2 pi epsilon naught. Then we have rho prime times A, which is lambda prime. And so lambda prime is v squared over c squared times the coefficient 1 over alpha times rho plus times the cross-sectional area A divided by R, and your quantity is times UR. So let's recheck that everything is there. F prime is minus q times E prime, so it's minus q over 2 pi epsilon naught. I'm already writing in the same fashion as in the first video on Lorentz force relativity without dual. So in the frame F that is. So this is the same prefactor we had there with the same sign. Then we have this factor v squared over c squared, which is dimensionless from here. 1 over alpha, in this case, we pick up an extra 1 over alpha. And then we have, and all this is part of rho w prime times rho plus times A divided by R, UR. So this equation here is the result that we get in the reference frame F prime for the Lorentz force on acting on minus q. If you go back to the video, to the first video of this series of 3, Lorentz force relativity without dual, the first video, you will find out that F prime is actually nothing but the F we found in that video in the first reference frame, simply divided by alpha. Now, if you were to assume, for example, that the velocity of the particle is much smaller than the velocity of light, then under these conditions, it so happens that the force F prime, you can simply convince yourself that this is true, because if I look at alpha, and in alpha I consider b to be very small, so it's like 0, so this gives me the square root of 1, so this is a factor of 1, F prime is approximately the same as F. So we found this beautiful result here, which tells us that in the small velocity limit, the force, the Lorentz force we find acting on minus q in the reference frame F is the same as the Lorentz force we find acting on minus q in the reference frame F prime. That is the principle which is we stated at the beginning of these 3 videos, the relativity principle from Maxwell's equations, that is Maxwell's equations are the same in any inertial reference frame, is true. We find the same result in the 2 reference frames. This also means that the electric phenomena and the magnetic phenomena are basically the same phenomena. Therefore, calling and describing this as the electromagnetic field together makes sense. In this relativistic sense. I find this quite amazing, that with very simple mathematical tools and very simple notions from 242, in the beginning of 342, we can establish this fundamental connection, this intimate connection between the electric and magnetic phenomena. This is the beauty of physics. So to summarize this video, Lorentz force relativity dual, we investigated the same problem as in the first video, but in the reference frame F prime, which is on minus q, that is minus q now is steady, the wire moves to the left, therefore there is relativity. We already found in the previous video the charge density associated with this wire, which shrinks and now becomes charged effectively. It was uncharged in the frame F. And so, by means of this relativity condition here, we were able to find the Lorentz force acting on this particle, which now is of electric type. By doing so, we found that it's exactly the same as the previous force in the case of small velocities. Okay? So the electric and magnetic phenomena are basically one and the same thing. That's it.